As a data scientist enthusiast, while going through different kind of literature, we often come across terms such as distances, similarity or dissimilarity, or let's say clusters and groups where entities exhibit similar or dissimilar behaviors. And we are often computing these distances for different kind of machine learning algorithms. The objective and goal of this video lesson is to take you through these distance metrics and actually show you how distances are computed in a 2D coordinate system. Before starting with this video lesson, I want to mention that 2D coordinate system and number lines have been covered in a separate video lesson earlier. So in case you are not familiar with those concepts, please do visit those video lessons before starting with this one. In case you're familiar with those concepts, but you want to brush up them again, it's never a bad idea to go and look at those videos and maybe join us in this journey. Let's start with this video lesson. Here, for illustration, I'm showing you a distribution of points, and these are again in 2D coordinate system. These are again in two-dimensional space. And I have a new point, and I want to do some analysis, which is find out for this new point, the orange point, which of the already existing points is most similar. Imagine this new point as a new customer, and you want to make recommendation to this new point or new customer based on the existing behaviors that you have seen for the existing customers. So imagine the already existing points as existing customers and they have their own unique behavior. And I want to analyze this overall information and find out and recommend for this new customer what kind of recommendations will be better to give so as to engage this customer better in my portfolio. So as simple as it can get, what I can do is look at the distance of this new point with all the existing customers. So in a 2D coordinate system, I need to find a way by which I can compute all the possible distances between all the pairs that exist between this new customer and the existing customers. Other than this basic example, I can show you other application areas where knowledge of distance computation really comes handy. What you see on the screen currently are examples of different kind of machine learning algorithms or application areas where computing distance really comes handy, whether it is finding similar entities or users with similar behaviors. It could be, again, an example similar to what I've already taken. Imagine Netflix or Spotify recommending new choices, new movies, new songs to new customers based on the behaviors of existing customers. And the idea is to find similar entities or similar customers to a new customer. And then recommendations can be made to those new customers. Similarly, while computing nearest neighbors, you can actually take an average of the behavior of nearest neighbors, such as computing the price of a house based on similar houses that are there in the neighborhood, based on attributes again, and then find out the average price of this new house. A very popular application of, again, distance computation and distance measures is k-means clustering, wherein clients define clusters, which is unique behaviors of customers, and distance metric is used to define these unique clusters. And a deeper understanding of how these clusters are formed and what are their unique behaviors helps the client make more customized efforts, make more customizations in terms of how they approach the clients. And that really helps the customers better engage with the clients in their portfolio. Let's now move to the part where we look at how to compute distances between points in a 2D coordinate system. The need here is to find distance between 2 points, given we know their coordinates. We can always imagine these 2 points falling on the hypotenuse of a right angle triangle, or let's say on the diagonal of a rectangle or a square. Let's take the first example, wherein let's assume that these 2 points fall on the hypotenuse of a right angle triangle. And our job next is to find out the third point of that right angle triangle and the other 2 sides as well. One of the sides we already know, which is A, B, or let's say the line connecting point A to B. And we need to find out the other 2 sides of this right angle triangle. I will first have vertical lines drop from both points A and B, and also a horizontal line pass across point A. And at the point of intersection, which is this yellow point, we find the third point of that right angle triangle. Now, by using some basic logic, we can actually figure out the coordinates of this point C. Notice that the point C is vertically below point B. Thus, this is going to have the x coordinate which is same as that of point B, which is 22. Also notice that the point C is at the same height as that of point A, which is where the y coordinate of this point is going to be same as that of y coordinate of point A, which is 10. Thus, the coordinates of point C are going to be 22 and 10. I've made a small copy of this triangle on the right hand side where I can show you how the distance AB can be computed by using a more familiar technique. The concept is called as Pythagoras theorem. Thus, we can compute the distance between points A and B or compute the side length AB of this right angle triangle by using this formula. And for this, we need the lengths AC and BC. Let's find out the lengths of sides AC and BC in this diagram on the left. The length AC is a difference of 22 and 10, and we need not take the difference of y coordinates because both are same, which is the same height, 10. So the difference of x coordinate comes out as 12. So this part is 12. On similar lines, we can compute the length BC, which is by taking the y coordinate difference between point B and C. So we subtract 19 and 10, and the difference that we get is 9. So this length is 9. And by simply plugging these numbers in the expression, we will get the length AB. You can also do the maths at your end and you will find that AB comes out as 15. Now these were all the computations pertaining to this specific example where point A and B had specific coordinates. The next step that we should really try out here is to find out a generic expression or a generic formula to compute distances between any 2 points given we know their coordinates. And that's what we are going to do now. First, I'm going to assign some generic coordinates to the points A, B and C. You can notice that point C does not have its own unique coordinates. Rather, these are derived using coordinates of point A and B. I will also show you in a separate example, once the orientation of points A and B is different, that we can still derive the coordinates of point C. Let's focus on this example for now. Using these generic notations, we can actually come up with a formula. First, we'll compute the distance AC and come up with a notation which is BX minus AX. We can also compute the distance BC and come up with the expression BY minus AY. And we simply plug these in the formula to get this expression. So the expression that you see out here is the expression that you use to compute distance between any 2 points in Cartesian coordinates or in 2D space. And all that you need is x coordinates of both the points, take a difference and square that up, and the y coordinates of both these points, take a difference and square that up, take a sum of those resulting numbers and compute the square root. Let's see one more example where the points are oriented slightly differently, but we'll come up with the same expression again. Here, notice the points A and B. They are not only oriented differently, but they also have different coordinates. We'll execute the same steps as done earlier. First thing is to drop vertical lines from the points A and B, and also a horizontal line such that the right angle triangle is complete and we have the third point in the right angle triangle. Then we find out the coordinates of this point C, which again can be figured out by using common logic. Since C falls vertically below A, the x coordinate is going to be same, which is 5, and this point is also at the same height as that of B. Thus, the y coordinate is going to be same, which is 8. Thus, the coordinates of point C are going to be 5 and 8. We again apply the Pythagoras theorem and use generic notation to come up with the expression. You can review this formula in more detail in case you do not have a hang of it yet. By plugging in the coordinates of both these points, we will get the final distance. And if you do it step by step, it comes out as 20. In the end, let's look at a few special cases where the same formula can really come handy, but this can also be done by some common logic by visually looking at the placement of points. So let's assume that the 2 points are located such that one is vertically on top of the other. And in this case, we only need to take the difference of y coordinates of these 2 points because they have the same x coordinate. So in the expression, the difference of x coordinate is going to give us 0 value, which is where we only engage with the y coordinates. In the other example, if the points are located such that they almost lie on a flat line, then the y coordinates of both these points are going to be same. Thus, we only compute the difference of their x coordinates, and that will give us the distance between the points. Like I mentioned in the very beginning, distance metric is very commonly used across different machine learning algorithms, and we covered in this video how to compute distances between 2 points in 2D space, or let's say in a Cartesian coordinate system. This fundamental knowledge will help you focus on learning the machine algorithm bit more once you encounter, let's say, a new technique. Often I've seen in my experience while teaching absolute beginners and especially learners who do not have a prior 10+2 mathematics background, they really struggle while learning the algorithm as well as the mathematics fundamentals together. I think this video lesson will help you focus on the mathematics bit for now, so that you go through and focus only on the machine learning algorithm bit and not the mathematical part of it, because that is what takes more time and focus.